Computers. They use this strange language called binary. What is it, and why do they use it? Well, let's start with the basics. It's common to think that binary numbers can only be a 0 or a 1. However, it's not so much the numbers that matter, but the fact that they can only be one of two opposite states. In fact, binary numbers can also be represented as true and false, black and white, high and low, or up and down. Anything with two states, really. Computers are electrical devices. Because of this, they are constrained to the physical limitations of two states, on and off, or 1 and 0. But I know what you're thinking. How can computers do so many things with just two states? Well, when a binary number is all by itself, it can't really do much. However, combining more of them together will allow us to represent more than just two states. A single binary number is called a bit, and a string of 8 bits is called a byte. The more bits you have, the higher you can count. This growth of states increases exponentially by 2 to the power of the number of bits. If you have 4 bits, you can represent 16 states. And if you have 8 bits, or 1 byte, you can represent 256 states. You get the idea. So we know how computers are able to count, but how can they do logic? Well, let's start small. I mean really small. Suppose we had 2 electric switches in series. For the electron to flow across the line, both switches need to be closed. If either switch were to be open while the other is closed, the electrons won't be able to pass through the wire. This is known as an AND gate. And the symbol we use for the AND gate kinda looks like a tombstone to me. If you have 2 switches in parallel, it doesn't matter if one or both switches are closed. The electrons will still find a way to get to the other end as long as both switches aren't open. This is an OR gate, and this is the symbol engineers chose to represent the OR gate. Long ago, when computers were starting to become a thing, they used relays instead of switches to create logic gates. Relays are almost exactly like regular switches, except they use electricity to control the circuit. This was done by having current flow through a coil of wire to create a magnetic field that would close the switch. However, this method wasn't used for very long because relays are big, slow, and prone to failing because they were mechanical switches. Computers would then later change to vacuum tubes, but those didn't last either due to their size, cost, and how fragile they were. It wasn't until the invention of the transistor that the computer would begin to take its modern form. Transistors were just a better choice in every way. They were energy efficient, really small, really fast, and not mechanical. On top of that, they are made of an abundant element called silicon, which is a semiconductive element that can act as an insulator or conductor when doped with other elements. You can kinda think of the transistor as a water valve. When the gate of the transistor has no voltage, electrons will not be able to flow through the transistor like a closed valve. However, if you give the gate of the transistor a positive voltage, the electrons will be able to flow through the transistor like an open valve. This type of transistor is known as an NMOS. And the other type of transistor I would like to talk about is the PMOS, which does the complete opposite of the NMOS. When the two of these transistors are arranged in series like this, we get an inverter, or a NOT gate. If I input a 0 into the inverter, it will output a 1, and when I input a 1, it will output a 0. We can also make an AND gate out of transistors, except it's much easier to make a NAND gate, which does the opposite of an AND gate. I don't want to go too far into the details of why this is, but a good rule to remember is that the PMOS transistor has to go before the NMOS. The transistors are still in series, just like the earlier AND gate example, but because the PMOS has to go before the NMOS, the output will be flipped. Putting an inverter after a NAND gate will flip it back to an AND gate, which takes more transistors to do. This also applies to OR and NOR gates as well. The reason why logic gates are so important is because when we connect them together, we can create a much more complex circuit that can do things like addition and subtraction. For example, this is an exclusive OR gate. Its logic is almost exactly like the OR gate, except it only outputs a 1 when both inputs are different. To create this logic gate, we can start with an OR gate since it's very similar to the XOR gate. If we then add a NAND gate and connect the two gates to an AND gate, we will get the final circuit for an exclusive OR gate. And the reason for this is the AND gate can only output a 1 when both inputs are true. If we look at the logic table for both the OR and NAND gates, you can see the only time both gates output a 1 is when the inputs are opposites, just like the exclusive OR gates. And if you want to make an exclusive NOR gate, which is a thing, just change the AND gate to a NAND to invert the outputs. When engineers design complex digital circuits, they use a branch of math called Boolean algebra to express logic in a much easier way, which I'll talk much more about in my next video about classical computers, where we will take all the gates we learned in this video and convert them into a mathematical language we can understand and dissect. And as always, thanks for watching, and I hope you liked this video and learned something from it. Peace.